Currently, we are solving for one-dimensional diffusion problem in porous media, and from the diffusion equation with x and t as the variables, we have derived this single ODE on C hat, right, where C hat is a dimensionless concentration and eta here is a dimensionless variable. So we have one parameter with one variable and with two boundary conditions, and we are going to solve for this equation now. Okay, so to find a solution for this, we will let's say define a parameter, or we will define phi, which is basically dc by d eta, right? This is just a temporary variable which we will use back in the equation. Okay, so this gives us the above equation in form of d by d eta phi plus eta phi equal to 0. Right, we have simply converted dc by d eta with phi, and that gives us this. And now if you want to simplify this further, this will become d phi over phi will be equal to minus d eta. So we have simply rearranged this equation, right? And now let's integrate it. That will give us log of phi equal to minus eta square by 2 plus some constant C1. Alright, so this is very straightforward so far, and we can actually define C1 as, let's say, log of C2. So in that case we can further rearrange this equation as log of phi over C2 equals minus eta square by 2, right? Which is quite straightforward. And now this will give us phi of C2 equals e to the power eta square by 2, or in other words, phi is equal to C2 e to the power minus eta square by 2. And now we will replace phi back with dc hat over d eta, and that is C2 e to the power minus eta square by 2. Alright, so we have got the equation back in form of c hat and eta. And now we will integrate this equation further, and that will give us c hat as C2 e to the power minus eta square by 2 plus, let's say, another constant C3, right? So C2 and C3 are constants of integration. Okay, so and to be able to find the concentration at a particular eta value, we must, so C hat at a particular eta, we must integrate it from 0 to eta minus eta square by 2 plus C3. Okay, so here C2 and C3 are constants of integration, constants to be determined, right? And to find constants C2 and C3, we must use the boundary conditions we have defined for a c hat on eta. And what are the boundary conditions? These are the two values we have. When eta is equal to 0, c hat is 1, and when eta tends to infinity, c hat is equal to 0. So that would give us, if we assume simply eta equal to 0, c hat is equal to 1, that actually tells us that c hat equals 1 is equal C3, because this term will simply become equal to 0 for eta equal to 0, right? And that's why C3 is simply equal to 1. Alright, and now that is condition 1, and we can also use condition 2 that says that eta is, as is eta tends to infinity, C hat is equal to 0. So now we can define C hat to be equal to 0 for C2 0 to infinity e to the power minus eta square by 2, and sorry, there should be a factor of d eta here which I am missing. Alright, so this factor of d eta was missing there. And now we know that C3 is equal to 1, so we can add equal to 1 here, and that tells us that C2 is equal to minus 1 over 0 to infinity e to the minus eta square by 2 d eta. Okay, this is what we get. And now, while this looks like an arbitrary integral, but if you solve for this particular integral or you try to calculate it using some software like MATLAB or some other software, this actually gives you a particular value of pi by 2. Okay, so this has a kind of a closed integral, right? It gives you a fixed value. So this is something we get either analytically or numerically, but this is the value, and that's why C2 can be defined as minus 2 over pi. Okay, so this is a value we have got analytically, or both analytically or numerically, and this is not an arbitrary value even if it looks like that. Alright, so this actually means our C hat that we have written here can now be written as C hat is equal to, C2 is now known, C2 is minus square root of 2 by pi. It goes from 0 to eta e to the power minus eta square by 2 d eta plus 1, right, where C3 is equal to 1. And that is why this actually gives us, let's write this as 1 minus 2 over pi 0 to eta e to the power minus eta square by 2 d eta. Okay, so this is the solution we get for the concentration, dimensionless concentration with respect to eta. And interestingly, what you see here, this particular form, that again is while it looks like something arbitrary, it's actually a function, and that function is known as error function. So this is called ARA of eta, and that is why an ERF basically means error function. So this is a well-defined function which is a name sounds funny, it's called error function, but it's a well-defined function. It has particular value for a given value of eta, and that is why this C hat is written as 1 minus ERF of eta. Okay, and interestingly again, 1 minus ERF is actually defined as ERFC. So C hat can also be written as ERFC of eta, where ERFC is known as complementary error function. Okay, and ERFC is always equal to 1 minus ERF. Okay, so this is what we have. This is known as error function and complementary error function. And now let's look at the values of error function and complementary error function. So these values, ERF has particular value at a given, or this function has a particular value at given eta. So if you say this is your eta, this can be called our error function of eta, and you can see as eta increases, error function increases in a particular way, and same thing is given here. So if you define your eta from here, this is, let's say, eta, this is your ERF of eta, and this one here is ERFC of eta. So you can see how your error function increases from eta equal to 0, and complementary error function decreases from 1 towards 0 with increasing value of eta. And that is why if you look at this equation or the solution that we have got, this is the solution that we got for given boundary conditions, right? These are condition, this is condition 1, this is condition 2. So at eta equal to 0, you can see your concentration here is equal to 1, and as eta goes to infinity, which you can see this value is not really 0 at any point, it becomes 0 only as eta tends to infinity, C hat is equal to 0, right? So it decreases slowly, and asymptotically it becomes 0. It's not exactly 0 at any particular location. Alright, so this is the solution we have got for diffusion of salt in porous media from one end, and this is the profile. This is basically the problem we are considering, where we assume that there is this salt concentration of C0 which is maintained constant at all times, C0, 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 right? And if you want to plot the concentration, basically it will look something like this. It's not coming perfect, but right, you can imagine how the concentration decreases. So at t equal to t1, it decreases within a small length scale. This is t2, this is t3. So it is decreasing within a small length scale for a smaller time. As time increases, the length scale within which the concentration goes from C0 to C equal to 0 increases, right? And then that can actually be understood from this plot here. So this is the error function, right? And what we know here is C hat is ERFC of eta. In other words, C over C naught is equal to ERFC of eta. Okay, and that is why it depends on eta, and eta, if you remember, depends on x over 2 dt. In other words, your x is equal to eta 2 dt. So now for t1, you will have different values of eta for a given, different values of x for given eta. T2 will have different value of x for given eta, and likewise T3. So as t increases, so T1 is smaller than T2 is smaller than T3. So corresponding x for a given eta, so x1 will be smaller than x2, will be smaller than x3 for a given eta. And that is why the concentration profile in this case that you see here, if this is C by C0 and you try to plot, it will look something like this. Okay, with different times your concentration profile will look differently. So this is a T1, this is a T2, this is a T3, and that is basically, it represents T1, T2 and T3 here, right? And likewise, if your flow continues, you will keep getting this broadened concentration profile, or thicker and thicker mixing zone between the salt water and fresh water, or between any fluids of different concentration. All right, so this solution that we have derived is for diffusion in one particular dimension, and while we are maintaining a constant concentration at one boundary, right? But depending on different conditions, let's say you are solving a two-dimensional problem or three-dimensional problem, this may have different solutions, but in most cases we see a diffuse interface between the one fluid with the other in case of miscible fluids. As you can see, the concentration is neither 1 nor 0, but the value goes from 1 to 0, right? And this diffuse concentration usually decreases in form of a error function at the interface, as you can see here. All right, so here once you have got the solution, you can actually easily convert that solution from non-dimensional form to dimensional form. So C hat is C over C naught, so this gives us C as C naught times C hat, right? And likewise your x, as we discussed, can be obtained from eta as 2 dt for given t value. So now if you, for a particular t, if you are able to define your different x value for different eta, that will give you concentration at different x location, okay, dimensional concentration. All right, and now we are going to see this problem in case of dispersion and also two-dimensional flow.